Welcome you to our next lecture. Today we're going to continue with quantum algorithms. So let me briefly recap what we did the last time. Last time we started discussing quantum algorithms. In particular, we've seen Deutsch's algorithm. And there the problem was to decide whether a function which has a 1-bit domain in a 1-bit range is constant or balanced, right? And we've seen that if we want to find out whether it's constant or balanced, and if we can only give a classical input to the oracle, and the oracle evaluates this function, then we know that we have to call this oracle twice in order to decide whether it's constant or balanced. However, if we are allowed to insert a quantum mechanical superposition, we have seen that it suffices that we only call this oracle once. So clearly we have a benefit if we use quantum mechanics. So if we can have a quantum mechanical input to this oracle. And today what we do is now we continue with Simon's algorithm. And Simon's algorithm provides us now with an example where we do have, where we see that quantum computation gives us an exponential speed up compared to a classical computation. Okay. So we again, in Simon's algorithm, we again work with an oracle. And now what we're going to see is that we will find out a very similar algorithm. And we see that if we only are allowed to input classically, then we need an exponential number of oracle calls for this particular problem, which is called Simon's problem. However, if we are again allowed to insert a quantum mechanical superposition, then we'll find that we only need to call this oracle a polynomial time in the number of qubits. Okay, so this, as our next section is 2.5.2, Simon's algorithm. So Simon's algorithm provides an example for an algorithm which shows that quantum computers can perform or can solve specific problems, can solve specific problems exponentially faster than classical computers. Okay, so now what is Simon's problem? So suppose now that we are given consider binary function. So consider a binary function which has an n-bit domain and range. So, and this function is again evaluated by the oracle. And it is promised to satisfy some specific properties. Namely that f of x is equal to f of x o plus s, okay, where for all bit strings x and an unknown bit string S. And this bit string S is for sure not the 0-bit string. And further, f of x is unequal to f of y for y unequal to x plus s. Okay, so what is this O plus? This is the addition modulo 2, so the bitwise addition modulo 2. For example, if x plus s is equal to y, then we have that xj plus sj modulo 2 is equal to yj. That's equation 108, and this is for all j's. Okay, so let me recap. We're considering a binary function with an n-bit range and domain, and this is evaluated by the oracle, and it's promised to satisfy that f of x is equal to f of x plus s for an unknown bit string s, right? And s is not equal to 0, and now the task is to find this unknown bit string s. So this is Simon's problem. The problem is to find this bit string s. So let me do an example first. Suppose now we have three bits. So n is equal to 3. Then let's do a table of f of x and x. So we have 000, then we have 1, 010, 011, then we have 100, 101, 110, and 111. Okay, then let's say f of x here is 101. This is 101, then this is 010. This is 010, then 000, then 1. So this is an example, and now let us find this unknown bit string for this example. So we already evaluated these functions for all inputs that are possible, right? This just give you an example of what this is about. And now we want to find s, okay? And now since f of x is equal to f of x plus this unknown bit string s, with f of 0 is equal to, okay, what's f? If we have the input 0, then we get 101. And we have the same input, we have the same output 101 if we input 110. So we have f of 000 is equal to f of 110. And from this, we know that s is equal to 110. Okay, so with this we found the bit string S. Now, so this was just an example, and we're going to do this now first with classical inputs. So as you can see by the example, each outcome appears exactly twice, right? And once we find two outcomes which are equivalent, we can deduce S by this fact. Okay? So meaning that we have to find 2 times the same outcome. And here, for example, f of 0, 0, 0 has the same outcome as f of 1, 1, 0. And then using that, this argument must be same as this argument plus S, we found S. Okay? You can do this with any other. For example, this one here, 0, 0, 1 gives outcome 0, 1, 0. And it has the same outcome as this one. Okay? And if you do from this 0, 0, 1 and 1, 0, 1, you can deduce S by the fact that this plus S gives this. Okay, so in words, we first note that by S is unequal to the 0 bit string, and that by X, O plus S is equal to X. We see that each outcome appears exactly twice. Hence, we must find 2 times the same outcome. To deduce S. Okay, so now consider that we only have classical inputs, right? In order to get 2 times the same outcome, we can first ask, okay, how often do we have to call the oracle? And then we see at maximum we have to call the oracle half of all possible outcomes plus 1. Okay, so it means it's 2 to the power of n divided by 2 plus 1. If we call this the oracle that often, then we can be sure that we found 2 times the same outcome. Okay, so the maximum number of oracle calls after which we find 2 equal outcomes is 2 to the power of n divided by 2. So this is half of all possible outcomes plus 1, which is 2 to the power of n minus 1 plus 1. And you see that this is exponential in n. Okay? Well, but this is only the maximum number. But what's the number in general, right? Does it also scale in general, exponentially in n? And in order to address this question, I do an example now, which should show you that indeed we need an exponential number of oracle calls. for the classical case. I'm not proving it explicitly. I'm just giving you now an example with which you can get a feeling that we indeed need an exponential number. And then I state the scaling behavior of the best known algorithm. Okay? So as an example, or in the general case, to see that an exponential number of oracle calls is needed in the general case. Suppose we call the oracle, suppose we call it 2 to the power of n quarter times. So this is now an exponential number in n. So we call the oracle 2 to the power of n quarter times. Then we find less than 2 to the power of n quarter squared pairs f of x, f of y. Okay, so from this number of calls, we find less than this number squared pairs, and we can now ask whether there is, or what the probability is that one of these pairs gives us the same outcome. And the probability for each pair to give the same outcome, f of x is equal to f of y. The probability is 2 to the minus n, meaning that in total, so the probability to successfully find S is then less than 2 to the minus n times 2 to the n quarter squared, which is 2 to the minus n times 2 to the n half, which is 2 to the minus n half. And you see that the probability is now exponentially small. So, meaning that if we call the oracle an exponential number of times, we find that the probability to get our unknown bit string S is still exponentially small, right? And from this you can see that indeed we need an exponential number of oracle calls to find S. Okay? So the best known algorithm it needs O2 to the power of n half calls. So, meaning that if we have classical inputs we need now an exponential number of oracle calls in order to deduce our unknown bit string S. So note that this is not a proof, but this should give you a feeling that it is like this. Because what we just showed is that if we call it an exponential number of time, then we still have an exponentially small probability to find S. And our next task is now to consider quantum inputs. And as we will see in a bit, if we have a quantum input, meaning if we can input superpositions to our oracle, then we only need a number which is linear in n. Okay, so we need a polynomial in n. And by this we then see that the quantum algorithm gives us an exponential speedup. So consider the quantum circuit. So this is the quantum circuit that we consider, and this box is now the evaluation of our oracle. So where UF performs the function evaluation which means the oracle call. UF acting on 0x, on x0 gives x f of x. Okay, so with this we can now go through the quantum circuit. So let's first calculate what the Hadamard is doing. So after the first Hadamard, we have 0, 0. We Hadamard the first register of n bits, and nothing happens on the second register. So we have then 1 over square root 2 to the power of n, and then a sum over all states x, and here we have 0. This is equation to 113. And after the oracle call, we get that okay, so this is now, first we did the Hadamard, and what the Hadamard does is it puts our first register in a balanced superposition of all states, right? And then we are calling the oracle, and this is actually, again, the same trick as we've seen in the Deutsch algorithm. What we insert here now to the oracle is a coherent superposition of all states, such that the function evaluation here is performed in parallel for all inputs, right? So this is the very same scheme as for Deutsch algorithm. And then in the end, after function evaluation, we now have to Hadamard again, as we see here. And what this does is it now uses interference such that we have constructive interference for our desired outputs. And then we perform the measurement. Right? So we are now here at this stage, and let us now first measure the second register. Okay. So suppose the measurement of the second register gives or yields f of w equal f of w plus s. Okay, then the first register is in state, or is in 1 over square root of 2, and then we have w, or w plus w plus s. So this is now the state of the first register after we measured the second register, right? So we measure the second register, say w, f of w, okay? And then we know there are exactly two outcomes, so two values of x which give the same outcome, meaning that the first register must be in the state of these values x which give the same outcome. Okay? What we now do is, according to the circuit, we now Hadamard again the first register. So performing again Hadamards on the first register. Gives the following state. So we have 1 over square root of 2 W plus W plus S, which gives 1 over square root of 2 Okay, what we want to calculate now is this Hadamard acting on some state. Okay, so let me calculate this as a side calculation. Now note that the Hadamard acting on W, okay, what is this? It's a Hadamard acting on W n minus 1 to Hadamard acting on W0. And this gives 1 over square root of 2, 0 plus minus 1 to the power of Wn minus 1, 1. So what the Hadamard does is if this bit is 0, then we get a balanced superposition of 0 plus 1. And if this bit is minus 1, we get 0 minus 1, right? So we can write this together as 0 plus and then a phase minus 1 to the power of this bit, right? And we do this now for all n bits. Then we get this tensor product, and we now combine this tensor product. So these constant factors give 1 over square root of 2 to the power of n, right? And then we have a tensor product, say j is equal to 1 to n, and then we have 0 plus minus 1 to the power of Wn minus j 1. Okay. And now let me write this as a general sum. So we have this gives 1 over square root 2 to the power of n, then this tensor product. And then we have the sum of let's call this x n minus j. And then we have minus 1 to x n minus j w n minus j, and then x n minus j. Okay, so this sum has now two terms. The term for x n minus j is equal to 0 is 0, okay, because here we have minus 1 to the power of x minus j. So if this is 0, then we get 0. And if this is 1, we get minus 1 to the power of wn minus j, 1. Okay, so it's exactly what's written here. And now we can write this tensor product. We can simplify this a bit and write this as a sum over all now x0 to xn minus 1, which go from 0 to 1, and then we have minus 1 xn minus j, sorry, n minus 1 times wn minus 1 times minus 1 x0 w0, and then here we have x n minus 1 to x0. Okay, this we can combine now. Okay, one more line. So what we did now is here we combined these phase factors and wrote this tensor product in this usual form that we have. And then you see that we are summing actually over all x from 0 to 2 to the power of n minus 1. And here we, in this exponent of the factor minus 1, we have x times w, where this x times w is this product, so it's a bitwise product. And then we can write this in this very nice compact form. And this we can now use in order to plug into equation 116. So this is now 117. And we plug this now into 116. Okay, I'm going to erase the circuit, and what you see, what's left is that we measure the first register, right? So we are now here calculating this Hadamard, and the only thing that's left is the measurement, right? So I'm going to erase the circuit now. So using 117 in 116, we get the following. So we get the state 1 over square root of 2, and then we have 1 over square root of to the power of n, and then a sum x equals 0 to the power of n minus 1, and then minus 1 x times w x, and then plus a similar term. And now we have here x times w plus s. This we can simplify, so with 1 over 2 n plus 1. Okay, so this is now the state of our first register. And you see that here we inserted this formula from 117 and here as well, and then we simply combined them. Okay? And as you remember from the circuit, what's left is measuring this, this first register. And you see, okay, if we measure, suppose now we measure z, x is equal to z. And then we know that minus 1 to the power of x times z must be the same. So this plus this, so this must be equal to this. Okay? This term minus 1 x times z must be equal to minus 1 x times z plus s. Because otherwise, this term, if this is not the same, then this would vanish. Okay? Because it's only plus 1 or minus 1. Means if the measurement of the first register yields outcome set, we must have that -1 set times W is equal to -1 set times W plus S, okay, which is the same as set times W modulo 2 is equal to set times W plus S modulo 2. So this leaves us with z times s modulo 2 is equal to 0. It's 120. Okay, so what we found now is we found a set such that z times s modulo 2 is equal to 0. That's what we got. Okay? And so let's write this down. By calling the oracle once, we find z such that z times s modulo 2 is equal to 0. You can now briefly think how many different possibilities of S can we rule out by this condition. Okay, think a bit about it. So you can think of like how many different S are there? Okay, in total there are 2 to the power of n. Okay, and now next we have to think about, okay, given any set, how many S are there such that if I perform this multiplication, do modulo 2, I get 0. Well, must be exactly half of them which satisfy this condition and half of them which do not satisfy this condition, right? Because here on the left-hand side I get either a number of 1 or 0, right? Because it's always modulo 2. And if I take all possibilities of S into account, I will see that exactly half of them fulfill this condition and half of them do not. Okay? So by this condition, I know that half of the possibilities of S, I can forget about them, right? I can rule out half of all possibilities of S. So what we do then is we do the same procedure again and call the oracle again. And we hope for an outcome which is different to this set, right? What I forgot to say is that you can only rule out half of them if set is unequal to 0, right? Because if set is the 0-bit string, then this is true for all, okay? So suppose now we have found such a set which is unequal to 0 and we ruled out half of them. What we do is we call the oracle again. We hope that we find another set which is different to this one. And from this, we can then rule out half of the remaining S, which means that in the end, we are left with 1/4 of all possibilities. and then we continue in this fashion. And in the end, if we found n minus 1 linearly independent sets, then we are left with two possibilities. Okay, we have then 2 to the power of n divided by 2 to the power of n minus 1 gives two different possibilities. And one of these possibilities is the 0-bit string. And we know, however, for sure that S cannot be the 0-bit string because this was promised. And this is how we find S in the end. Okay? So let me write this down and do a short example. Suppose we call the oracle more often. Such that the chase call returns set j. Then given that set 1 is not the 0-bit string, by set 1 times S equals 0 modulo 2, we can rule out half of all possibilities. For S. Then by measuring set 2 unequals set 1. Again, set 2 is not the 0-bit string. We can further rule out half of the remaining numbers. For S such that we are left with 2 to the power of n divided 2 to the power of 2 possibilities. And then proceeding similar, by measuring n minus 1 linearly independent set j, we are left with 2 to the power of n divided by 2 to the power of n minus 1, which is two possibilities. For S, one of them is S equal, one of them is 0 to the power n, or however, since we know we are promised that S is not the 0-bit string, we found S. Okay, but how often do we have to call now this oracle? And it turns out that we can get a probability exponentially close to 1 if we call the oracle O n times. Okay, so this can be accomplished with probability exponentially close to 1. By O(n) oracle calls. Let me now come back to our previous example in order that you see this procedure. Okay, this is quite formally now. So suppose now we again have this example of a register of n equals 3 bits, right? And then suppose now we do this quantum circuit, and what we get out is Z1 is equal to 001. Okay, so we see this is not the 0-bit string, so it's fine. And what we then check is, okay, we check all those possibilities of S, which are 8 possibilities, perform this multiplication and check whether this modulo 2 is equal to 0 or not. Okay, so we have then Z1 times 000 is equal to 0, and then Z1 times 001 is equal to 1. Z1 times 010 equals 0. Z1 times 011 is 1. 1 times 1000 0. 101 is 1. 1100, and Z1 times 111 equal to 1. Okay? With this we can now rule out half of the possibilities. So we know that S cannot be this one, it cannot be this one, and not this one, and not this one. Okay? So from this we know that S must be element of 0, 0, 0, and then 0, 1, 0, and 1, 0, 0, or 1, 1, 0. Okay? So this was Z1, and now we measure again. Say we measure Z2, which is equal to 1, 1, 0. Again, this is not the 0-bit string. Well, and then we calculate Z2 times 0, 0, 0, which gives 0. Z2 times 010, which gives 1. Z2 times 100 gives 1, and Z2 times 110, which gives 0. Okay, and from this, again, we know that it's not this possibility and not this one. So we get that S must be either 0, 0, 0 or 1, 1, 0. But we know that S is not the 0-bit string, and with this we find that S must be 1, 1, 0. Okay? So this is the same S as we've had in the example in the beginning, and this should illustrate this procedure, that we first measure one output, and then we can forget about half of these possibilities. So we have half of them, and we measure a second output, which is different to the first one and also not the bit string. Then again, we can rule out half of them until we are left with 2 possibilities. After n minus 1 such, we are left with 2. One of them must be the 0-bit string. However, we can be sure it's not the 0-bit string because this we are promised. And from this we can deduce S. Okay, and in order to get n minus 1 such linearly independent sets, we have to measure O n times. Okay, so this is now polynomially in n. And as you see, in the classical case, we found that we need an exponential number of oracle calls. And here, with this quantum algorithm, we see that we can solve Simon's problem by only a linear number of oracle calls, so a polynomial number. And from this we can conclude that this specific problem, which is Simon's problem, can be solved exponentially faster on a quantum computer as compared to a classical computer. Okay, I think this is a good time now to do a break, and let's start again in 10 minutes. Let us now continue with the second part of today's lecture. So in the first part we've seen Simon's algorithm. There we've seen that there can be, or there are some specific problems. One of them is the Simon's problem, where quantum computers can be exponentially faster compared to classical computers. And now we are continuing with quantum phase estimation. And quantum phase estimation is an algorithm, or let's say a subroutine of many algorithms. So it's key for many algorithms. And one of them is the prominent Shor's algorithm for factoring numbers. And here in this lecture, we now discuss this phase estimation, which is a subroutine of Shor's algorithm. And in the exercises, you will then go a bit further into Shor's algorithm. And I think you do an exercise which goes in this direction, that you do even factor a small number, I think. Okay, so let's continue now with phase estimation. This is chapter 2.5.3. And phase estimation is key for many algorithms. Such as solving the order finding problem, or the factoring problem. Okay, the problem is stated very simply, namely the problem of phase estimation is as follows. So suppose we have an oracle suppose a unitary U has eigenvalues, or has an eigenstate U with eigenvalue e to the I 2 pi phi, where phi, which is between 0 and 1, is unknown. Okay, and the problem is finding this phase phi. The task is to find phi. Okay. It's actually very simple, the problem. You're given a unitary. The eigenvalues of unitary must live on the unit circle, right? So we can always write this as e to the I some phase. And we write this now as e to the I 2 pi phi, where phi is between 0 and 1. And our task is to find this phi. And what we suppose now is that we are given an oracle And the oracle can create this eigenstate u, and it can also evaluate this unitary u and powers of this unitary u. Okay, by powers I mean u to the power of a integer number. Suppose we have oracles capable of preparing u and performing the controlled uj operation. So it's u to the power of j, where j is a non-negative integer. Okay, so you might wonder why we again have these oracles, right? So in this case, as I told you, phase estimation, as I show it here, can be rather seen as a subroutine of some algorithm. And what we suppose is that you can find a circuit which can efficiently perform this controlled U operation and create this eigenstate, right? So we leave this as a task for the specific algorithm that you want to do in the end. For example, if you do Shor's algorithm, then you will see that preparing such an eigenstate is not a problem, and performing such controlled unitaries can be done efficiently, right? And for general, in phase estimation, we say, okay, there is an oracle which can do this. And if you want to apply phase estimation for some specific problem, then you might have to think about, can I perform this efficiently or not, right? So as I said, for Shor's algorithm, you can do it efficiently, but here we don't care because we are just interested in whether we can do phase estimation, okay? Whether we can find this phase phi. Okay, so consider now the following circuit. So we have a register with 0 states, which we Hadamard. And then here we have this eigenstate U. Okay, this can be a bundle of bits. And then we perform such controlled unitary operations. So this is U to the power of 2 to the power of 0. And then here with U and 2 to the power of 1. And then U 2 to the power of 2. And here we have U and 2 to the power of n minus 1. Okay, and this, we abbreviate this circuit as follows. We Hadamard the first, and then we have a controlled unitary. So these controlled unitary operations, we simply abbreviate the circuit in this way. So that's the 2.121. Okay, so what you see, what we do is we have here a register of n qubits initialized in 0. And first we Hadamard them all. And then we perform controlled unitary operations. Okay, so this one controls a unitary where u is taken to the power of 2, to the power of 1, sorry. Then this is taken to the power of 2, then u to the power of 4, and so on, until we are at u to the power of n to the power of 2 minus 1. Sorry, u and then 2 to the power of n minus 1. Okay. This is the circuit. So the first part of the circuit, and this is how we illustrate it. The reason is that there is a second part that we discuss in a second. So first, let us discuss this first part. So let's calculate what's happening here. First, what we do is we Hadamard. So the Hadamard acts as 0 u, and then we Hadamard the first register. Again, we have such a state. And then we do the controlled unitaries. So we have 1, 2 to the power of n, sum. So we have a unitary u to the power of 2n minus 1, which is controlled by this bit on the top, which is, say, the bit kn minus 1. And then we have u to the power of 2, 1, which is controlled by the bit k1. And u to the power of 0, which is controlled by k0, acting on u. Okay, and now we use that this is an eigenstate with the eigenvalue e to the I 2 pi phi, right? So this gives us e to the I 2 pi phi times 2 to the power of n minus 1, and then controlled by k n minus 1. And this e to the I 2 pi phi to the power of 1 k1, and this e to the I 2 pi phi to the power of 0 k0 u. Okay, now we can combine all these phases. Okay, so we combined now these phases and by this sum. And here what you see is that this is nothing else but k. Okay. nothing else but an expression for k as a decimal number, e to the I 2 pi phi k times u. Sorry, I forgot k. It's here. Okay, so this is what we get out of this circuit. And what we do now is we consider a second part of the circuit. So next, we consider an inverse Fourier transform on the first register. And this followed by a measurement. Hence, the circuit is this one to 121 extends to, so with 0 n bits, then with u, we had here our Hadamard, then this controlled unitaries. Now we do an inverse Fourier transform and then a measurement. Okay, and we do nothing on the second register. And since we do nothing on the second register, we can forget about it. So we can now focus on the first register because nothing is done anymore in the second one. So as I said, we can drop the second register because we're doing nothing there anymore. So to calculate the outcome, let us drop the second register. And act with the inverse Fourier transform on the first register. So we have then the inverse Fourier transform acting on the state or on the first register of state 2, 123. So then it's 1 over 2 to the power of n. Then k equals 0 to 2n minus 1 e to the I 2 pi phi k. And then we have k. Let us calculate this now. So this is a linear operator. So we can write this in this way. And now we know what f dagger k is. So it's, I think it was equation 288, okay, somewhere there. So we get then 1 over 2 to the power of n, sum over k j equals 0 to n minus 1, and with e to the I 2 pi k times phi minus j divided by 2 to the power of n j. Okay, so note that the sum here is now running over j and k, because the sum over j is coming in due to the Fourier transform. And then we have this phase e to the I 2 pi k j divided by 2 to the power of n. This comes from the inverse Fourier transformation. And then this state j. Okay, now finally what we do is we do a measurement. And we write the outcome the following way. The outcome 2 to the power of n phi tilde. Okay, where this phi tilde can be written as a binary fraction 0.phi tilde n minus 1 to phi tilde 0, such that 2 to the power of n phi tilde is equal to phi tilde n minus 1 to phi tilde 0. Okay, note that, so this, why do I introduce this notation here? The reason is that the phase that we want to estimate, phi, lives between 0 and 1, right? But we have now n bits in order to, so we want to perform a measurement, we're measuring n bits, and we want to get some value of phi, right? But phi lives between 0 and 1, and not between 0 and 2 to the power of n minus 1. So what we do is we multiply by 2 to the power of n, such that this number 2 to the power of n phi tilde is now a n-bit string. However, if we drop this 2 to the power of n, we get phi tilde, which is 0 point something, and this is smaller than 1. So this lives between 0 and 1. And by this, we introduce this notation in order to get phi tilde, and phi tilde will be then in the end our estimation of the phase. So this appears with the probability. So the probability to get the outcome 2 to the n phi tilde is equal to this state. How should I write it down? Okay, it's 2n phi tilde, and then the state here. Okay, so this is the probability. What we use is actually simply Bourne's rule. And now we can calculate the inner product of this one with this one. So it's 1 over 2n k j 0 So this gives us a delta j 2 to the power of n phi tilde. So meaning the sum over j vanishes, such that we're left with the sum over k. And we have e to the I 2 pi k, and then phi minus phi tilde. Okay, and we are rewriting this a bit. As e to the I 2 pi times phi minus phi tilde to the power of k. And now you see that we can use the geometric series. So here you see that this is nothing else but the geometric series. And for this we know the solution. So using the formula for the series, which is sum k equals 0 to n, say x to the power of k, which is 1 minus x to the power of n plus 1 divided by 1 minus x. So let's use this here, that the probability for 2 to the power of n phi tilde is equal to 1 over 2 to the power of n, and then we have 1 minus e to the I 2 pi times 2 to the power of n phi minus phi tilde, and here 1 minus e to the I 2 pi phi minus phi tilde. Okay, let's rewrite this a bit. So here we put out a factor e to the I pi times 2 to the power of n phi minus phi tilde, and then we have e to the minus I pi 2 to the power of n phi minus phi tilde plus e to the I pi . And similar here. Okay, and then we see that this is almost the sinus. If you introduce a 2i, then we get the sinus. But since we have it on both in the numerator and in the denominator, this 2i doesn't matter. And this is only a phase factor, which cancels due to the modulus, right? So we can write this as 1, 2 to the power of n, and then the sinus of pi 2 to the power of n phi minus phi tilde divided by the sinus of pi phi minus phi tilde modulus square. Exactly. Okay, now it depends on whether phi, so whether this phase phi, so this is what we want to find, right? And now we can ask okay, what's coming out here, and we have to discriminate two cases. The first case is that the case that we can express phi exactly with n bits. Okay, and the second case is that we cannot express phi exactly with n bits. Okay. In the first case, if we can express phi with n bits, then we can measure phi with certainty. Okay. However, if we cannot express phi with n bits, then there's no way that we can exactly measure phi, because then we can only approximate phi, right? Because we cannot write it down with n bits. So let's first consider the easiest case, meaning that we can express phi exactly with n bits. So if phi can be expressed exactly, or can exactly be expressed via n bits, then equation, where is it? Here, equation 2, 126 gives that the probability to find 2 to the power n phi, okay, so if we can now express phi exactly with n bits, and then the probability that we get phi tilde is equal to phi, then here this vanishes, okay, we have here 1, meaning this gives 1 over 2 to the power of n, and then the sum over k equals 0 to 2 to n minus 1 times 1 modulo squared. Okay, and what is this? The sum is 2 to the power of n divided by 2 to the power of n is equal to 1. So meaning we find phi with certainty. It is, we find phi with certainty. Well, that's great. But as I said, the second case, if we cannot express phi exactly with n bits, then we can never find phi with certainty, okay, because we cannot express it. And however, what we can do is we can find an approximation of phi. Okay. So if phi cannot be expressed via n bits, we can only find an n-bit approximation of phi. Okay, now let me show you that we do find an n-bit approximation which is close to phi with high probability. Okay. To see that we find with high probability an n-bit approximation phi tilde, which is close to the optimal n-bit approximation. Phi tilde opt. Let's note that phi minus phi tilde must be smaller one, such that so we want to find a good approximation now. And the best approximation that we can find is this I called phi tilde opt, the optimal n-bit approximation, right? And this would be the value phi tilde, which coincides with phi for the n bits that we have, right? But phi itself may be more precise. You may need more bits in order to get the exact value of phi, but phi tilde opt coincides in the first n bits with phi. So this is our optimal approximation. And what I want to show now is that we get with high probability a good approximation. So given this, that phi minus phi tilde is always smaller to 1, right? We have that the modulus of sinus pi phi minus phi tilde must be smaller or equal to pi phi minus phi tilde. And equation 130. Which one is it? This here, 2127 becomes, let's insert this here, that p 2 to the power of n phi tilde, it's now smaller or equal to modulus of sine pi 2 to the power of n phi minus phi tilde divided by 2 to the power of n, and then we have here pi and phi minus phi tilde, which is nothing else than the sinc function, squared sinc function of pi 2 to the power of n phi minus phi tilde. And we know, since in the limit x is equal to 0, the sinc function, so sinc of x is 1, we see that we get a good approximation, a good n-bit approximation of phi with high probability. Okay, so this is a nice way how to see it, that it must be true, right? Because what we get out is well approximated by the sinc function, right? And you know the sinc function has a very high peak at 0, and this means that we have with very high probability a approximation. So phi tilde is a good approximation of phi with high probability. And we can also calculate now what's the probability for the optimal n-bit approximation. So for example, for phi tilde equal phi tilde optimal, we have that, okay, phi minus phi tilde optimal, the difference must be smaller or equal to 1 to the power of 2n plus 1, because they coincide in the first n bits. Okay, both are binary fractions, so the first n bits on the right-hand side of the dot coincide. So meaning the difference must be smaller or equal to this number. And accordingly, we have that sinus of pi 2 to the power of n phi minus phi tilde. So the modulus of this greater or equal to 2n plus 1 phi minus phi opt. This must be optimal. So this approximation is possibly not so easy to see. What did we use? Where we used that the modulus of sinus of x is greater or equal to 2 modulus of x divided by pi for x in minus pi half to pi half. Okay, we can illustrate this actually. So the modulus of the sinus gives us something like this, and then we have 2x. I'm running out of time. So this function here, this is 2x pi, and this is sinus of x. So this is this approximation that the sinus of x is greater or equal to this function in this interval, and that we use now, such that using this equation here, 128, and yields that p of 2 to the power n phi opt is greater or equal to yes. Okay, so we used this approximation in this formula here for the sinus, and then we get this expression, and then the 2's cancel, so we have 2 to the power of n plus 1 divided by 2 to the power of n. It's missing here an n. So the 2 to the power of n cancel, and what we get is, what's left is 2 divided by pi, and then we have the square, meaning 4 divided by pi squared is approximately 0.4. So we see that the optimal n-bit approximation we get with a very high probability, right? And this is to the reason that all n-bit approximations which are close to the optimal also appear with high probability, according to the sinc function. So in summary, what we've seen is now that we can do quantum phase estimation, and if we can express this phase phi exactly with n bits, then we found an algorithm where we can exactly get this phase. And if this phase phi cannot be exactly expressed with n bits, we get a good n-bit approximation with high probability. Okay, with this, I'm at the end for today's lecture, and I see you next time on Thursday. Thanks.